In this video, we're going to talk about a connection between the derivative of a polynomial and the possibility of it having multiple roots. And that connection is captured by the following theorem. So the theorem is, suppose f is a field and f of x is a polynomial in f adjoint x. Then there are two equivalent conditions. One condition is that f of x has a multiple root in some extension of f, and the other condition is that f of x and its derivative have a common factor in f adjoint x. So I'm going to write that down and then just make a remark about how interesting this theorem is. Okay, so then f of x has a multiple root in an extension of f if and only if f of x and the derivative of f of x have a common factor. And I should really be clear, a common factor doesn't mean just any common factor, because of course any two polynomials have a common factor, like one would be a common factor. So what I really should say is a common factor of positive degree. There we go, that's much better. In f adjoint x. All right, so what makes this theorem kind of miraculous is that it allows us to tell whether f of x potentially has a multiple root in some field extension of f, like the splitting field of f of x over f, just by looking at common factors between this polynomial and its derivatives over the base field, so in f adjoint x. So we don't even have to look at an extension field of f in order to determine whether f of x has a multiple root in an extension. That's kind of wild if you ask me, but we're going to prove that in this video. All right, so the proof has two parts. This is an if and only if. Let's begin with this direction. This direction requires a little bit of care, because we need to show that there is a common factor between f of x and its derivatives, but we need to show there's a common factor in this ring here. So let's begin by assuming that f of x does have a multiple root somewhere, maybe not in f, but in some extension. So suppose f of x has a multiple root in an extension e over f. Okay, and let's go so far as to call that multiple root alpha. Now let's interpret what it means for f of x to have a multiple root alpha. That means that f of x can be factored into x minus alpha to some power, I'm going to say squared right now for reasons I'll explain in just a moment, times g of x for some g of x belonging to e adjoint x. Okay, now I may not be able to do this in f adjoint x, but I can certainly do it in the extension field where alpha exists. Okay, so why squared? Because I never said that alpha has multiplicity 2. What if it had multiplicity 3 or 4 or 7? Well, in any of those cases, I could still factor out x minus alpha squared and leave the remaining factors of x minus alpha for g of x to absorb. That would be perfectly fine. All I need to make the argument is to know that x minus alpha squared is a factor of f of x. All right, so let's proceed. So then, what is the derivative of f of x? Well, I can calculate that using the product rule. The product rule says the derivative of this whole thing is equal to the derivative of this times g of x plus this times the derivative of g of x. So let's write that down. The derivative of x minus alpha squared is 2x minus alpha. And you can actually, that's not using the formula exactly, but you can verify that that's true using just a little bit of algebra. Okay, times g of x plus x minus alpha squared times, I was going to say d prime of x, but let's use the terminology we're using, the derivative of g of x. If you like using g prime of x, that's fine. I prefer to use this official notation that we totally made up. Okay, and what do we notice about all of that? That all has a common factor of x minus alpha. So that's x minus alpha times 2g of x plus x minus alpha times the derivative of g of x. All right, so what does that mean? Okay, now you may think, well, there we have a common factor. X minus alpha is a factor of both f of x and the derivate. So we're done, right? But not so fast. We said there's a common factor of positive degree in f adjoint x, and this factor may not belong to f adjoint x. So we need to show that there's some common factor of positive degree, and that's going to take a little bit more work. But let's think about one thing that we can take away from this. So takeaway here is that alpha is a root of both f of x and its derivate. That's actually going to be crucial later on. Okay, so now I'm going to think about what are the common factors of f of x and its derivate. I'm going to think about that in a fairly algorithmic way that is characteristic of how we think about these things in number theory, and that's using the division algorithm. Okay, so in number theory, if you want to figure out whether two numbers have a common factor other than 1 or -1, we use some algorithm for finding their GCD. And one algorithm is you can prime factor both of them and then figure out if there are any common prime factors. But for polynomials, that may be rather hard. But another way we can find common factors, if they exist, is by using the Euclidean algorithm. So that's what we're going to do here. So let's zoom that over. There we go. Okay. So now this is like part 2 of the argument. All right, suppose we use the Euclidean algorithm on f of x and the derivative of f of x. Now I'm going to do it in that order, divide f of x by its derivate because the derivate has smaller degree. So we would get f of x equals the derivate times some quotient, which I'll call quotient 1, plus some remainder 1, where the degree of the remainder is less than the degree of the thing we divided by, which was the derivate. So that's step 1. And I'm going to keep performing this process until I reach a point where the remainder is 0. Okay, so let's just write down a couple of steps of the process just as a reminder of how the division algorithm works. All right, so then I divide the derivate by the first remainder. And remember, that's just how the Euclidean algorithm works, is we pull that next remainder over and divide by it. Get another quotient, quotient 2, and another remainder, with the new remainder having smaller degree than the previous one. Next step, we pull over R1, we divide it by R2. Hungry cat. Okay, and now we just keep going until we reach a remainder of 0, which eventually we will because the degrees of the remainders keep decreasing, and they're natural numbers, so they can't decrease forever. So eventually we will get r sub, let's say r sub k minus 1 of x equals r sub k of x times a quotient, which will be quotient k plus 1 of x, plus 0. Now at this point, we will have that rk of x not only has smaller degree than rk minus 1 of x, but actually divides the k minus 1th remainder. Now let's think about the possibilities for what could happen here. Okay, so what is this last non-zero remainder, rk of x? If it has degree greater than 0, sorry, that should say degree there, it's kind of sloppy looking. If it has degree greater than 0, well, let's just think about what that would imply for this whole process. So if I have this polynomial, rk of x, that has positive degree and divides r sub k minus 1, then that means, well, let's write down the previous step of this process. That'll help us figure out what it means. Okay, so the previous step would have been rk minus 2 equals rk minus 1 times the kth quotient plus the final non-zero remainder, rk. Okay, so let's look at that step. So we know this is certainly divisible by rk because it is rk. And we're saying that this is also divisible by rk. So then what does that mean? Then that means that this remainder also has to be divisible by rk because both terms on the right are. So then we could step back to the previous step in the process and show that rk minus 3 is divisible by rk of x. And then rk minus 4 is divisible by rk of x. And then you get the idea. These are going to keep cascading back. We're going to get r3 of x divisible by rk, r2 of x divisible by rk. So then this one has to be, well, this is divisible and this is divisible, so the derivate's divisible. And r1 was divisible and the derivate was divisible, so f of x, all of these are divisible by rk of x, the final non-zero remainder. And that should make sense if you think about the result of the Euclidean algorithm. The Euclidean algorithm tells you that the last non-zero remainder is the GCD, greatest common divisor, of the two objects that we began with. Okay, so if rk of x has degree greater than 0, then we're done. Since this final non-zero remainder has to divide both f of x and its derivate. Now you may wonder, well, wait a minute, this rk of x that you came up with, is it really in f adjoint x? Or did I jump out into e adjoint x at some point? Well, for this, just think about how the division algorithm works. Remember, the Euclidean algorithm is just repeated iterations of the division algorithm. And when you use the division algorithm on polynomials both from f adjoint x, the whole process only involves f adjoint x. It doesn't take you out into a field extension. So everything in this picture here belongs to f adjoint x. All of this. So that means I've got rk of x is a polynomial in f adjoint x. All right, so that's great. We're done, right? Oh, well, wait a minute. We only addressed one case. If the remainder has degree greater than 0. What if we get a remainder, the last non-zero remainder, and it has degree equal to 0? Then we're in trouble, right? So what if rk of x has degree 0? Okay, then rk of x is a constant. So let's call that r, and that's an r belonging to f, and it's non-zero, because otherwise it wouldn't be the last non-zero remainder. There we go. Well, in this case, let's go back and review what the Euclidean algorithm was doing. So go back and review the steps. And this time we're going to go back with a view to the fact that alpha was a root of both f of x and its derivate. So go back and review the steps with that alpha in mind. So if I just look at this process, I know that alpha is a root of f of x. I'm going to use a different color to indicate this now, so let's use green. So alpha is a root of this. If I evaluate that at alpha, it becomes 0. Same with the derivate. Alpha is a root of both of those. So this evaluates to 0 at alpha. This evaluates to 0 at alpha. So r1 of x must also evaluate to 0 at alpha, because if you evaluate the whole equation at alpha, we need to get equal values. This is 0 and this is 0. So this would also better be 0. Same with the next step. This evaluates to 0 at alpha. This evaluates to 0. Therefore, this must as well. And inductively, you can go through and see that every step, each remainder has to evaluate to 0, including rk of x. So inductively, we can show that each r sub j of x has alpha as a root. Okay, so then if rk is a constant and it's non-zero, we've got a contradiction. Since rk of x is a non-zero constant, I guess I'm not going to end up using that little r there. That's okay. And has alpha as a root. That's just not possible. When you evaluate that polynomial at alpha, you get r. Ah, there we go. Now we use the r. All right, so we have a contradiction. Therefore, our k of x can't have degree 0. That last non-zero remainder has to be of positive degree. So reviewing the argument, the only possibility is that we end up with a non-zero remainder of positive degree, and that ends up being a common factor in f adjoint x of both f of x and its derivative. So I think we are done with that part of the argument, and now this video is about 15 minutes long, so I think we'll move to another video for the other half of the argument.